order up to model, a motivating example. In this topic, we will use an example of a supply chain for a product called an in-sync pacemaker by a company called Medtronic. A pacemaker is a device that is put inside the body of a person to help control abnormal heart rhythms. It is usually installed in surgeries in hospitals. And we're going to consider the supply chain for this pacemaker. And the supply chain will have three stages. The stages that we will focus on will be there is a manufacturing facility that delivers the product to a distribution center somewhere in the United States. And then there are about 500 sales representatives scattered across the United States that deliver the product to hospitals. So the manufacturing facility delivers to the distribution center once a week, right? Order is made once a week, and then delivery is done sometime later. And then each sales representative checks their inventory once a day and requests an order from the distribution center. And then the lead times, which are the times between from the moment a particular party requests an order to the moment they receive an order, the lead time is different between the manufacturing facility and the DC. It's 3 weeks. And then lead time between the DC and the sales representative is just 1 day. This is actually, by the way, the purpose of the distribution center. Right? The distribution center brings the product much closer to the sales reps and therefore provides them with a much more response in terms of lead time. If a sales rep needs 1, 2, 3 units of this pacemaker, when they order it, they receive it 1 day later. Right? The lead times here is 1 day. And the distribution center keeps larger quantity, and when it has a low level, it may order from the manufacturing facility, right? It can send an order once every week, and then it will receive those units 3 weeks later, a much longer lead time, but this is a much higher quantity, and there is some aggregation of demand here at the DC level. So for this, we will consider the distribution center as the whole, but we will also focus on one of the sales representatives. We will consider Susan Magnotto's territory, and Susan Magnotto is one of those representatives. She serves demand in several hospitals in her area, and she has to deliver the right pacemakers to those hospitals. So the pacemaker, the in-sync pacemaker that we're considering is just one type of the product. You have to keep that in mind. So the objective here, because the gross margins are very high, meaning that whatever the price of the pacemaker, a large percentage of it is the profit that Medtronic and the whole supply chain is making out of the sales. The lost profit would be the lost opportunity from sale if we had a stock out. So we don't want to have stockouts because we don't want to have any lost sales. Not only we can lose profit here in the initial sale, in the immediate sale, but we might also have disappointed, medics or hospital administration, and they might say, let's shift to another supplier, perhaps, who will provide us with better service. So because of this, we want to have a system that manages this inventory in the supply chain that will provide very high service level, right? We want to target very high service levels, something like 99% in stock probability or 99% fill rate. When we consider the distribution center, we can look at the demand for the in-sync pacemaker in all the, across the whole country. And this here chart shows us in bars the monthly shipments, which, assuming we satisfy all demand, will be also monthly demand for the pacemakers. And you see they are of the order like 100, close to 200, up to 500 units every month. And you see also the end of month inventory, how many units of the in-sync pacemaker they have, the line, the blue line here. And so if you do calculations on actual data that's behind this chart, we will find out that the average monthly demand is 349 units. Remember, this is all the units sold across all territories, right, through about 500 sales representatives. And we can also find out that the standard deviation of this demand is 122.28. So because the distribution center orders weekly, right, we need to convert this demand to a weekly demand. Now, assuming every week or weeks are independent from each other, right? So we will assume the demand between weeks is independent, and also will assume that each month on average contains 4.33 weeks. We can actually divide monthly demand by 4.33 to get a weekly demand average. And because we're assuming independence, the standard deviation of the weekly demand will be standard deviation of the monthly demand divided by the square root of the number of weeks per month, 4.33, which will give us these numbers. So these are some numbers I will later want to use, but they describe basically the demand forecast for the future. We're assuming that the demand is varying, but the rate it doesn't change. The parameters, statistical parameters of this demand do not change over time. When we turn to demand in a territory, remember we will consider Susan Magnotto's territory. The demand, of course, is much smaller. It's just one of 500 territories. So this chart shows us the sales in a territory with bars. And you see the sales are actually quite small, 2, 3, up to like 14 units. Notice that we do not assume any seasonality here, as you might try to see a pattern of increasing or decreasing demand through the months. We will be assuming the variation here is purely random. And also remember, we assume the sales are equivalent to the demand because the assumption is we do not lose any demand. All the sales are satisfied. We have enough units in stock to satisfy all the sales. So if you again think about the data that's behind this chart, if you calculate the total demand in Susan's territory, you find out it was 75 units, or on average, it's 75 units per year. And also, we need to convert it to per day because for later on, when we actually consider the model and Susan orders, checks inventory and orders once a day, we have to convert this demand to daily values. So for that, we need an assumption of how many days Susan works per year. And we will assume there are 52 weeks per year when Susan works, and she works 5 days per week. She doesn't work the weekends. So her operating days will be 52 times 5. And if you divide the annual demand by the number of days per year, you'll get daily demand. In this case, we just calculate the average daily demand. And we will not calculate the standard deviation because the assumption here is that we will be using Poisson demand distribution for this product. Now, why are we going to use Poisson demand distribution instead of normal? Well, the reason for this is that normal distribution doesn't work very well for items that are moving very slowly, like this pacemaker in one territory, right? On average, just a fraction of a pacemaker is sold per day. So this is a demand that has a very small average, and for that, normal distribution is not very useful because normal distribution assumes there is a variability and there is some symmetry in the variability, right? So the values below the average and above the average somehow have the similar distribution. But when the average is so small, close to zero, that would mean we would actually have significant probabilities assigned to negative values. And of course, these values cannot happen in reality. So for that, we will use a Poisson distribution, which works better and is asymmetrical with small mean values.